Thank you very much for the introduction. Thank you very much for the invitation. It's an absolute delight to be here. And it's an absolute delight to be talking about what I will be talking about, at least for me, maybe, hopefully also for you. And yeah, apologies for the late arrival. All right, so I think it's also I'm particularly happy to be here because I'm going to talk about a lot of work that was happening here by you and Corfus. And so it's kind of, this is always work that's been very impressive to me, that I've always like checked in the archive, and it's kind of exciting to be able to be here to tell you about your own work, and then you can correct my mistakes. It's a good way of learning. All right, so maybe a quick, so my title is GEMS. So this is Geometry of Enumerative Mirror Symmetry. So yeah, I can write that down. So Geometry of Enumerative Mirror Symmetry. And so I'm gonna, yeah, what do I mean by this? So the theme will be, actually let me ask a question. Among people I don't know, how many of you are like maybe symplectic geometers? How many of you are like algebraic geometers? Yeah?
They're the same. Are they the same?
They are the same? It was a trick question. You should study more. And I guess everyone is maybe doing a bit of mirror symmetry then as well, yeah. Okay, so very good. So the theme is, so we want to, I'm going to present examples of IMS implies EMS. So we're going to turn.
I'm actually here, right?
What's that?
I'm actually out in speed.
That's right. Absolutely. And EMS is, I don't know, enumerative mirror symmetry. So we all know that enumerative symmetry derives from this institute. So I will present examples of this. That's right. Absolutely, yeah. So IMS can also stand for intrinsic mirror symmetry. Okay, I should push out as much as I can the moment my handwriting gets bad. So intrinsic mirror symmetry, so which is a program that's been developed by Gross, Siebert, and then GS et al. So this ties also really well with the lecture series by Pierrick and Julia, because they will also be talking about this. But though my interest is in a different is a bit different from what they will be talking about. All right. So an EMS stands for enumerative mirror symmetry. So in some sense, main examples. So I said present examples of. Maybe I should say this. What do I mean by this? By this I mean compute Gromov-Witten invariance via periods, period integrals. So this is just genus 0, Gromov-Witten invariance via period integrals. So it's probably the case that, it is definitely the case that in all examples I'm going to be talking about, you know how to do this much faster than what I'm presenting. But the hope is that by developing this more general machinery, we will be able to extend it to a much more general case. So the main example, or main examples, will be Y a Del Pezzo surface, D smooth anticanonical, And then we have the pair y comma d, which is like log Calabi-Yau pair. Log Calabi-Yau variety. This is also equivalent to the local Calabi-Yau threefold given by the total space of K, Y. So by equivalent, I mean there's many statements this equivalence can be stated. You can state an equivalence of genus zero Gromov invariance. This goes back to Takahashi, Gartman. I had a paper on this with Graeber, Rudat, and then there was various extensions. If you're interested in higher genus, there's a paper by Pierrick, Longting, Huagui, and Honglu. And then another way to phrase this is their mirror constructions are the same. There's many ways this can be phrased. So I will be talking about this mainly, though there are extensions to like more general Fano varieties, etc. If you at any point want to just look at one example, that I mean, you could just be looking at P2E, right? So this is, you know, may look at this one. And so the principle will be, if you understand like some examples really well, that will help you to generalize. Maybe let me put some features. Let me tell you about some features. Or I should also say, maybe like a main reference. So there's a so joint work. So there's a joint work with Rudat and Siebert, which should be, you know, it's on the archive this week. So it should be on archive soon. Archive this week. So it's, I mean, this week. I mean, it's yeah. I'm not in charge of archive submissions, so, but yeah. I can also send it to you if you want it. So I will be talking in particular about some joint work with them. All right. So the features. So the plus side. The plus side is that our approach removes computations. So what do I mean by this? The way that mirror symmetry, let's say traditionally is done, is we have two varieties that are supposedly mirror to each other. We compute something very complicated on each side, and we find that it's the same. So we're going to get rid of this. We want to have a theorem that states that the generating function of Gromov-Witten invariance is equal to a period integral and without using any computations. By the way, if you could also check, so you could also check, so there's a series of articles that I like very much. I don't remember which one it is, but so one is Conan, Kwokwe, Lao, Tseng. So there's various combinations of these. That was like 10 years ago, so I'm still catching up. but if you wanted to like read a bit about these questions, you could look at like there are two papers, I think. Yeah, one is enumerative meaning of I don't remember the title. Sorry. Mirror maps. Yeah, okay, fantastic. One is enumerative meaning of the mirror maps. Thank you. Maybe the other one is SYZ mirror symmetry for toric Calabi-Yau threefolds, maybe. Yeah. So those would be some excellent references to look at. In fact, I learned about this when Kwokwe gave a lecture series in Korea, like last decade, and then yeah. Thanks. I'm still stuck there. Sorry. But I will also talk about some more recent work that was done at IMS or CUHK. But that's a start. All right. So the advantage is it removes the computation part. It's closer to the physics reasoning. original physics reasoning. So if you read, it's always interesting if you talk to some physicists, the way they think about mirror symmetry is a bit different. And for them in particular, having two moduli spaces, one a Kähler moduli space, the other a complex moduli space, is really important. And so we'll be also reviewing some of this. In the model language, this would be like Coulomb and Higgs branches. So we want to be something that is more closer to, let me say this one more time, which is that physics had a very beautiful geometric reasoning of why mirror symmetry holds true. And as mathematicians, we kind of, we just turned it into like huge computational algorithms. So I kind of want to go back to this like beautiful description that we used to have. And then it also gives some simple geometric proofs to known results. And generalizations. Let me give you a little taste of this. In this context, we have this geometry, but we also have D, which is a it's an elliptic curve. And then there are various results that link the Gromov-Witten theory of the three of them. And so using our formalism, you can give geometric proofs of these results, which is, I find, very satisfying. So I'll also talk a little bit about this. Another example is if you take the work by Pierrick, Longting, Hongluo, and Schwagrey, you see that the inverse of the generating function of the invariance, the genus zero Gromov-Witten invariance of local P2 is a modular form, and then this kind of follows relatively easily from our formalism, which is something that I will also say something about. Okay, so those are the plus points, but it's also not everything is happy in this picture. So as of now, this is still a proof of concept. It is relatively limited. And if you wanna be very mean, you can say that it shifts the difficulty. For example, in the case of Del Pezzo surfaces, the mirror symmetry becomes a question of finding suitable degenerations of Del Pezzo surfaces. In higher dimensions, it becomes a question of finding suitable degenerations of like Fano manifolds, and those are hard problems. So we, in some sense, we shifted the difficulty. All right, but the hope is that this is still evolving, and the hope is that we'll get better results as we develop this. So what's my plan? So I will start by reviewing a string theory prediction. For Calabi-Yau n-folds. This is just to, I'm a little bit worried that everyone knows this in their sleep. And if that's the case, I apologize. Well, I kind of want to like go back to the 80s, the 90s, and then like move forward to like explaining why we get to the point that we get to. So in particular, this will motivate smoothings. This is not a smoothie. This is a motivate This is like being able to smooth normal crossings varieties is very important for this program, or for mirror symmetry in general, and we want to kind of review why that is. So I'm also going to like state, I may do this like today or relatively early, or I may do this later, which is state known results for P2E slash KP2. This is to give you some like knowledge of some results that we are after. Then I will probably introduce IMS as this fantastic place to do research via some examples. I'm hoping that these examples will build some intuition of what intrinsic mirror symmetry is about. I think Pierrick and Julia will also give an introduction, but I think it will be complementary. And I will also review some results in enumerative geometry. So results / constructions. In enumerative geometry. So I'm hoping to give you a proof of quantum Serre duality, which is something from the 2000s, but something that you will see becomes geometric once you apply intrinsic mirror symmetry to it. So I will then give some introduction to IMS for pairs y, d, where maybe y is Fano and d is smooth anticanonical. And so this is this joint work with Rudat and Siebert. Again, this will be a bit different from the setup that Pierrick and Julia will be describing. And then at the end, I want to show how IMS, how this implies EMS. For YD. And at this point, I will also mention some more recent results by people at IMS. In particular, correspondences between Lagrangians on the mirror side and sheaves supported on hypersurfaces on the Fano side.
What dimension?
Yes, so there are, good question. So there are, part of this works in every dimension, part of this only works for dimension 2. So I will aim to give a all dimension explanation, so I will not limit myself in dimension, but it will use some inputs, which is in particular, the input you need is a degenerations of the pair of a Fano variety, smooth anticanonical divisor, and those are hard to construct. So there will be some input to the construction, and then also the EMS results on the other side, if you do it in higher dimensions, are more limited. But some results, so there's like a mixture between two. Sometimes you need to specialize dimension, and sometimes it works in general. So you can see that this is still a bit of, this is why I said this is more proof of concept, and there's still plenty of directions to take this to. Yeah. This will be presenting, I will mainly be presenting the results with Rudat and Siebert, but also some extensions that I did with my PhD student, Kimberly. and maybe some extra things as well. All right, questions? All right, fantastic. I have also print out of the paper here if someone wants to take a look. All right, so let's predictions of physics. So we're gonna like review some results of physics, and I think they will motivate what we'll be doing next. So at this point, I hope I'm not helping you to sleep. Actually, if you do sleep, that's not a bad thing. I encourage you, but I think it's useful to like review it and then that will motivate what we do afterwards. So, all right. So review from physics. So predictions from physics. So we take a compact Calabi-Yau n-fold. So it has trivial anticanonical bundle. I mean, in the examples, you can think about local Farnow varieties. For example, local P2, which is not compact, but that's fine. So then a deformation of X is a family with a central fiber X0. The central fiber should be isomorphic to X, and if as a complex manifold you want this to be proper holomorphic submersive. As a right, you could just require it to be flat, and surjective, submersive, and then B will be some small ball. So in differential geometry, this would actually really be a small ball. In algebraic geometry, you might take some Artinian rings or some other local rings, and so what we're really doing is we're doing first order deformations. All right. And then, given such a deformation, we have a Cordero-Spencer map. So it takes the tangent space of B at 0 to H1, XTX. So H1 XTX, so to obtain a deformation, you're changing the complex structure. So the complex structure is how local charts of the tangent bundles are gluing together. And so it makes sense that you would have such a map. And so this classifies first order deformations. Moreover, if your deformation is locally universal, or just universal, so I mean, if you locally universal, if it gives all the local deformations, then existence of this is guaranteed by existence guaranteed by results of Tian and Friedman. So then this implies that actually the tangent space is isomorphic via this Cordero-Spencer map to H1 XTX, which is Bogomolov-Tian-Todorov theorem. Okay? So this, as a consequence of this, you can build a local, you have a local moduli space. Of dimension so this is a local moduli space so these are deformations of X of dimension. So this is equal to the dimension of this, and because we're Calabi-Yau, T of X is isomorphic to omega n minus 1, so the n plus 1 alternating product of the cotangent bundle. So this means that this dimension is h of n minus 1, 1, so the Hodge number of X. Well, I'll write it just like this.